talk is by Professor Lech Longa on the Lebwohl-Lasher model of liquid crystals from quadrupolar to spontaneously induced chiral order.
Thank you, Peter. It's quite a pleasure to talk at this workshop, and I would like to thank the organizers for inviting me. In my talk, I would like to concentrate on symmetry issues. There are two platforms with which symmetry issues can be well discussed. One is, of course, Landau-Desjens sort of theory, and I would just talk about Landau-Desjens as well as about the second platform, namely Lebwohl-Lasher models. Lebwohl-Lasher lattice models of liquid crystals are perfectly issued to implement symmetry aspects, and that will be most of my talk. So let me start with some definitions. Actually, I'm in a very happy position because Epifanio introduced most of my notation, so you know, it's much easier then. The Lebwohl-Lasher model was introduced in this famous paper of 1972. This paper appeared just after the Meyer-Saupe mean field theory came into market. And the Lebwohl-Lasher asked themselves the question, is the mean field solution of any value? Can we actually test this solution against fluctuations? What happens when we introduce more, so to speak, sophisticated approach which takes into account, let's say, all statistical mechanical machinery? And the simplest way to introduce this machinery, let's say, in the case when we are speaking of orientational degrees of freedom only, exclusively, is to place the molecules on the lattice. Say it could be a cubic lattice or any sort of lattice. Let's stick to cubic lattices. Sorry, it's not visible. On my computer, I can see it better, but here somehow it disappeared. So believe me, it's a cube, elementary cube, and the molecules are placed in the lattice sites. And well, you can then assume that they interact pairwise, additive, and suppose that the interactions are restricted to nearest neighbors. If you do so, and if you disregard the interaction between intermolecular vector and the molecules, then actually you end up with many-body generalization of mean field Meyer-Saupe theory, which is simply the interaction between molecular axis of uniaxial quadrupolar moment, as you may remember from Epifanio's lecture. So it's simply minus epsilon sum over nearest neighbors P2 cosine theta ij. And the Vij can also be written down in the tensorial notation. Dots in my talk would mean a total contraction over Cartesian indices. So the first thing that appears is that this sort of interaction, of course, preserves the infinity H symmetry of nematics. And therefore, it should somehow resemble what Meyer-Saupe did. Assuming the lattice structure means that actually the orientational structures that are predicted by the model not only characterize nematics, but can also characterize smectics, columnar, and perhaps crystalline structures. Okay? This model does not pay attention to the translational degrees of freedom at all. And let's now see how this model compares with what Meyer-Saupe calculated. Clearly, it predicts isotropic to uniaxial phase transition. And if you look at the numbers, you see that all the parameters are kind of overestimated by mean field. But really bad estimation is for the transition entropy. The transition entropy is from simulations about 5 times smaller than the one coming from Meyer-Saupe model. But you see, so actually, simulations show us that the transition is even weaker first order than the one predicted by mean field. Well, actually, these models are also very nice to test other sort of approximations. The model is really simple, which is not apparently seen from this notation, but if you write it as a scalar product of two vectors, it's actually the simplest possible parameterization of the model. It also shows you that Lebwohl-Lashers are just generalizations of spin models, classical spin models. And I will explore that in a while. So now, because of the simplicity of the model and because of correctness in accounting for symmetry, this model, even though we know that at present all lattice simulations are very natural and possible within computational power, even though this model still attracts because of its simplicity and because of the possibility of coding the symmetry. And here are some possible avenues of generalizations which were explored in the literature. So inclusion of higher Legendre polynomials, investigation of confined geometries, let's say with surface grating and with patterned surfaces, effects of external fields, electro-optical devices, and interestingly, chiral liquid crystals were also looked at with this sort of modeling. Then I saw some papers on polymers and elastomers. And what is interesting, there is a great deal of work devoted to low-dimensional systems, especially to two-dimensional systems. What appears interesting, as you know, in two dimension, when the Hamiltonian is characterized by global continuous symmetry, let's say O2, then there is no true long-range order, but we observe something which is called topological phase transition, Kosterlitz-Thouless phase transition. Interesting thing is that when you release the molecule and allow the molecule to have O3 symmetry, full O3 symmetry, then you can even, at least that's what follows from recent works, you can even remove this topological phase transition from the statistical mechanics. So actually, there is a great deal of work devoted to that. As I said, lattice models explore orientational order, and within this frame, my talk is limited. There is also a very important aspect of Lebwohl-Lasher models, namely, if you discretize Landau-de Gennes or Olsen-Zoher-Frank energies, you immediately end up with a kind of Lebwohl-Lasher model. Actually, when you do that with Landau-de Gennes theory, you can recover a part of models I'm going to discuss soon. Now, there is also another important aspect. Suppose that your theory is about, well, suppose it's about hard roads. When you do density functional, then your excluded volume is multiplied by one particle distribution functions and integrated over allowed degrees of freedom. Now, if you explore the symmetry of one particle distribution function, namely you study phase transition to nematics or to higher symmetric phases, then your excluded volume averages out over all unimportant, so to speak, degrees of freedom. And what is left is actually symmetry allowed terms, terms that are allowed by the symmetry which is implicit to one particle distribution. And because of that, you get effective model which very much resembles that of Lebwohl-Lasher. For instance, the famous Ansager model, when applied to uniaxial phases, in the lowest order just shows up the same structure as a Lebwohl-Lasher model. In other words, if you just replace temperature by 1 over rho for hard roads, then you actually get a mapping between the two. So that was the introduction. And now, in my talk, I'm going to concentrate on biaxiality issue and the symmetry of biaxial interactions. And then I will switch over to a rather controversial subject nowadays in the literature, namely how to get spontaneously chiral states out of the theory. You know that spontaneously chiral states are observed in bananas and in flexible dimer molecules. So I will concentrate on that issue in the second part of my talk. And if time allows me to do so, I will tell you something about splay twist band deformations that can be predicted by this sort of treatment. So first, I will tell you something more about biaxiality and about the biaxial symmetry. It will be extension, actually, of what we have already heard from Epifanio. If you just start studying a problem of biaxial order, you can start just blindly by assuming that your molecule, whatever it is parameterized by a tripod of orthonormal vectors, say B1, B2, and B3. The same is for the second molecule, except for the names are L1, L2, L3. So I have B molecule and L molecule. Suppose these two molecules are of D to H symmetry. Then immediately you end up with the simple form of interaction, which is generalization of the interaction which was on the previous transparency. Namely, it's a just scalar product of all vectors involved. So you have B alpha, L beta for all molecules squared. You easily recognize that this interaction is indeed D infinity H symmetric. Each molecule has this symmetry by assumption. But if you do that, you end up with 6 parameters, which is too many, of course. And Straley already in his fundamental paper showed that only 6 parameters really matter. And that can easily be seen. Namely, if we have here a quadruple moment of D to H symmetry, then this quadruple moment can be decomposed in the so-called spin matrices, L equal to spin matrices, which are second moments of interactions. And we know from the theory of spin representations that there are 5 such matrices corresponding to L equal 2 and M equal 0, M equal plus minus 1, and M equal plus minus 2. When you symmetrize these matrices, you end up symmetrized with respect to D to H symmetry, you end up with these two tensors, which is uniaxial one and the biaxial one. Nice thing about these tensors is that they are orthonormal. Dot means a contraction over Cartesian indices here. And now, with this knowledge, you can go back and decompose these terms in terms of the basic vectors. And of course, then you arrive at a much simpler expression, which already has only 3 coupling constants, and that was the one shown by Epifanio. But if you work a little bit harder, you find out that all off-diagonal terms, so alpha different than beta, just can be eliminated. And actually, what you get at the end of the day is just the interaction between B1, L1, B2, L2, and B3, L3. It can't be simpler, right? So that's the most general, actually, interaction for D to H symmetric molecules. And with this knowledge, you can do statistical mechanics just by tracing over orientational degrees of freedom of your interaction. But if you find something like that, then, let me quote Epifanio, to avoid unnecessary computation, you can still check as whether there is some intrinsic symmetry in this interaction. And indeed, there is. And actually, we were quite surprised studying this problem in 2005 that no one has really explored that before. And what sort of this extra symmetry is in this interaction? The symmetry is simply a possibility of exchanging the axes, as trivial as that. If you just exchange B1 with B2, L1 with L2, etc., I mean, you do it globally. For all molecules, the same operation. Then you should arrive at the same interaction. But of course, the coefficients in front are different. And actually, if you work that symmetry out, you get a non-trivial contribution, non-trivial information coming from this exchange operation, namely the so-called duality transformation. It's an exact property of this model. It says something, and this duality transformation means the following. In my exact statistical mechanics calculation, I always have something like beta times Hamiltonian, right? So actually, one of these three parameters which are here could serve as giving a scale for the temperature. So suppose that this temperature scaling parameter is omega 2, 0, 0. In other words, the moduli of that parameter, which I denoted V0, is just dimensionless temperature. Then actually I'm left with two extra parameters, which are V2 and V0, and the sign of V00. So that's the general symmetry allowed interaction. And now, if I do exchange the axes 2 and 3, so I will exchange B2 with B3, and L2 with L3, etc., then to having partition function invariant with respect to this operation, I have to rescale temperature according to this prescription, and the remaining two parameters according to that one. If I do that, my partition function is left invariant. So actually, this allows me, so you see here these areas. So for instance, the area A, subject to this operation, goes into A23. C goes into C23, D into D23, etc. So actually, it's sufficient to study the model in the area A to get full information about what's going on in the area A23, etc. The most interesting thing in this transformation is the self-dual line. At this line, these points, these lines here, are left invariant under this transformation. And that means there is some intrinsic deep symmetry which is in this formalism. And you can easily imagine that these are Landau points of the theory. So actually, around this line, the molecule is neither uniaxial nor, it's neither prolate nor oblate. So actually, along this line, you get a line of Landau points. Actually, the area A corresponds to prolate-like molecules. They could be biaxial or uniaxial, but prolate-like. So that's actually the story behind this model. And it's very useful because it allows actually to construct the full bifurcation or full phase diagram of that model irrespective of the parameters that you take. And that's illustrated here. If you combine the information coming from symmetry with the bifurcation analysis of the mean field equations, then you end up with the following diagrams. Namely, when the sign V00 is 1, then we have disk-like states in this area of parameter space and rod-like states in this parameter space. Here we have the line of biaxial states. And here is a direct phase transition from the isotropic to biaxial. It's perhaps better presented in the three-dimensional diagram where we have temperature, V0 and V2 on one diagram. surface tailed with large squares separates isotropic phase from uniaxial phase, while the one tailed with small squares separates uniaxial from biaxial. So you see, here is the Landau line, here is the line of a direct phase transition from the isotropic to biaxial nematic, but you also here have an island of biaxial states. And what is more, you have also a line of tricritical points, and an example was shown by Epifanio previously. So this model was just explored by many, and here's some literature, relevant literature to that. In my talk, I would like to actually limit myself to the dispersion model. The dispersion model is the simplest version, simplest non-trivial version of the previous analysis, and it corresponds to the gray line in this bifurcation and duality phase diagram. It's this one. You obtain the dispersion model if you assume simply geometric mean rule for the interactions, or the so-called Berthelot rule. Then, apparently, it amounts in replacing those tensorial products which were on the previous transparencies by a single product of two biaxial tensors, Qi and Qj. And these biaxial tensors are combinations of the uniaxial tensor, that is this one, and the biaxial one, that means this one. This is the model of the interacting quadrupoles explored by Zanoni's group, and here is the solution. You see, this point is exact. It should exist, it should be recovered in any sort of approximations, because the duality symmetry is exact for the statistical mechanical model. And that's this point. And that's the direct transition from the isotropic to nematic. Well, it's sufficient to do simulations in this area, actually. This area, then, is reproduced. So that means this small area here, I mean, this line, actually, here, corresponds to this area in here. And this area is just a duality transformation of this line to this regime. And it's also a good way to check the results of simulations, because you can actually first do duality transformation to this result and then check whether these results are compatible with your simulations. So that's the first part. I will use this dispersion model in my further analysis, but now I will show you how to, well, actually this has been discussed already extensively in the literature. So now I'm going to show you that adding the so-called octupolar interactions to quadrupolar ones, which were present in the model, you actually can account for ambidextrous chirality, which is recently observed experimentally, especially in banana systems. But let me start in a systematic way. So first, definition of chirality. This issue has been addressed in the famous Baltimore lecture of Lord Kelvin already in 1884. Namely, two objects are achiral when, say, these objects are achiral in the sense that when I mirror image this object, I can easily, by performing translation and proper rotation, bring them to coincidence. So bringing the objects to coincidence means that they are achiral. If I can't do that, then they are chiral according to the definition. And for instance, cogwheels are chiral because you cannot bring this image into coincidence by performing translation and proper rotation. It's important. Proper rotation is involved, not the rotation of general kind. Now, a standard chiral molecules endow their chirality because of chemistry. Namely, you have tetra-coordinated carbon atom, and if you attach 4 different groups to it, the mirror image of this group does not coincide by means of proper rotation with the original segment. So that means if I have something like that on my molecule, then say prolate-like molecules cannot acquire anymore in their ground state a parallel configuration, because that would be a achiral configuration. So in order to somehow take trace of chirality, these molecules become misaligned, and the misaligned angle is a measure of chirality, as we know. And that's standard way we have chirality in our system. But what surprises is that you can also get chirality breaking from non-chiral molecules. And I will show you some experiments on that. Namely, this sort of chiral symmetry breaking has been observed for bent core systems and also for bent mesogenic dimers. And the observation was very simple. Namely, you cross polarizers. You observe your sample under cross polarizers. And when you decross it clockwise or anti-clockwise by the same angle, then you see that the intensity of the domains just interchange. So you see bright domains become dark and vice versa. But the structure of the domains becomes invariant subject to this operation. That has been observed in smectic B phase, for instance. And that might not be so surprising, because smectics, the so-called B phases of bananas, many of them are chiral in nature. But what was really surprising was the observation of the same phenomenon actually in nematic phases. So you see this is the same actually picture, but in the nematic phases. Now, there are there are many possible explanations of that fact, but there are 2 actually existing in the literature. Namely, they were interpreted as self-assemble of twisted conformers. Here are the simulations of such a self-assemble. This sort of mechanism was suggested in this paper and also by some experimental works. And the second possibility was that actually what you observe here are twist bend deformations. And that was suggested first by Kresse, Peltz, and the colleagues, and by Memmer. But now, the question is how to account for such a situation, how to describe it at the level of symmetry. And of course, this is a very controversial subject, and probably there are many possible solutions. Well, some of them are more preferential than the other. I would like to tell you about one of them. Let me start first just to clarify the problem. Let me start first with the standard Landau-de Gennes picture of chiral structures. A chiral structure is seen optically. So chiral domains are in the range of visible light, so they obey the areas of few thousand angstroms. So most probably the reasonable way to describe them is the mesoscopic one, where we just refer, say, to alignment tensor. And here is the standard Landau-Ginzburg-de Gennes theory of nematics. You have trace q squared, trace q cubed, trace q squared squared, etc. This expression is absolutely stable given that the ratio of the elastic constants is greater than minus 2/3. I wrote this expression in dimensionless form to emphasize that the model actually has only 2 parameters, relevant parameters, dimensionless temperature and the dimensionless elastic constants. All other parameters can be removed out from the theory after proper rescaling. So that's actually the first part. An interesting thing is that when you go to uniaxial limit with the Q tensor, you immediately recover Osen-Zoher-Frank sort of expression where this term will be just sum of splay squared, twist squared, and bend squared with the same coefficient proportional to average value of P2, while this one is S squared plus B squared. Here's the notation. So the first term is just d alpha q beta gamma times d alpha q beta gamma plus Einstein's summation convention involved. So I sum up over all repeated indices. This term is just divergence of q, which is d alpha q alpha gamma, d beta q beta gamma plus Einstein convention applied. Now, that's for non-carial system. If you switch over to cariality, then you need to add, let's say in this minimal coupling theory, you need to add one extra term which has this totally anti-symmetric Levi-Civita tensor. And of course, this guy changes sign when we change the parity of the system, parity of the tripod of the vectors describing tensor. So you have q alpha mu d beta q gamma mu times epsilon, and it's non-zero. Now, kappa is, of course, the material parameter. Now, you may ask, is it easy to see that indeed this theory describes cariality? Well, there is a nice thing about this formula, namely, if you take quadratic part of this free energy density, this one, this one, this one, and this one, then you can diagonalize it if you go to the Fourier space. And this diagonalization is simply by the so-called helicity mode expansion. Namely, you expand Q in Fourier modes, and M's are just these matrices indicated here. These are just spin L equal to tensors. Now, if you do that, here is the visualization of those modes times exponent I chi r. So you see M equal 2 mode is just spiraling biaxial box. M equal 1 mode is a spiraling biaxial box, but the box which is under non-zero, under the non-zero angle with the k vector. This is the k-axis of the system, and this angle is different than the 90 degrees. And finally, M equals 0 is just compression mode, compression and extension mode. As these matrices, as indicated already, are orthonormal. Now, if you substitute this expansion to your formula, then the quadratic part gets diagonalized. And because of the diagonal form, and here is moduli of the k vector, so each k mode can separately become diagonal with these matrices. And you see, you get something which is linear in k and quadratic in k. And actually, the most promoting mode is M equal 2. Then this is the minimum and disappears. And here you get the minimal value as well. So for given sign of k, you have M corresponding to this sign which minimizes. So you have left-handed or right-handed spiral depending upon whether k is positive or negative. And this expression predicts you that you have a non-zero k vector, so you have non-zero wave propagating in the system. It's M equal 2, which is most probable. For instance, holosteric phase in this picture can be described as the uniaxial mode plus the biaxial spiral. And here you have some coefficients which you have to find from the minimization. So at the level of quadratic free energy, things are quite easy. The problem starts when you introduce nonlinearities in here. So trace q cube and trace q squared squared. But as far as we can say, as for today, this model perfectly describes holosterics, and also it can describe blue phases. Although I'm not aware of exact analysis of the ground state of this model for arbitrary A and rho. And kappa, of course. This is quite a challenging problem in statistical mechanics. So if we agree that indeed the model takes into account cariality, then the question comes, where does the totally antisymmetric tensor come from? So kappa times epsilon. In the case of ordinary materials, a qualitative answer has been given in these two papers, and we more or less understand what's going on. But now, how about non-carial molecules? Again, where does the totally antisymmetric tensor comes from? The answer to that question has been, at least one possible solution to that question has been given by Tom Lubensky and Leo Jagiellonski in this 2002 paper, where they simply showed explicitly that in order to get biaxiality, and I will show you in a while why in order to get cariality, I would like to repeat, I mean spontaneously induced cariality, and the cariality which does not fit the sign of kappa. Namely, I should get, with the same formalism, left-handed and right-handed spirals. In order to get that, just for symmetry reason, you need extra order parameter, which is just the octupolar tensor. This octupolar tensor can be calculated for hard-rod molecules as well as for dispersion interactions. A first mention of octupolar tensor in the literature has been given by Fell, and actually he analyzed the model in the mean field approximation. Now, so if you assume that the physics, say, of bent core systems and flexible dimers, in addition to quadrupolar tensor, needs also octupolar tensor, and probably the dipolar field. In bananas, we have the dipoles, of course. We have steric as well as electrostatic dipoles present. So if you take these three order parameters into account, then of course theory becomes terribly complicated, complex, and here is the full web of possibilities that you get out of that. And that was actually actually produced by Tom Lubensky and Leo Jagiellonski. Now, you can imagine the degree of difficulty to get all these structures at the level of Landau-Desgen's theory. That's one thing. Especially because of the chiral structures appear here at the end of the hierarchy. So in order to get it from standard Landau-Desgen theory in some systematic way, it is quite formidable undertaking. And I will show you that situation simplifies tremendously if we treat this sort of idea with the Lebwohl-Lasher type of interaction. Now, but first let me explain you why cariality is induced by the presence of quadrupolar and octupolar interactions. This cartoon exemplifies this issue. If I have quadrupole and no, if I have, say, quadrupole without octupole moment, then of course quadrupole is perfectly mirror symmetric. If I have octupole, then as well it's perfectly symmetric. But when I combine a molecular property, that means quadrupolar and octupolar together, then it appears that when I do mirror image and try to bring these objects into coincidence by a proper rotation, I will never succeed. Either I can bring these two to coincidence, but then these two will be misaligned. And vice versa. If I bring into coincidence these two, then these two will be misaligned. So this simple cartoon explains why indeed chiral can be induced by the presence of quadrupolar and octupolar tensor. But there is still one more non-trivial thing. This quadrupolar tensor must be biaxial. If it's uniaxial, so imagine that you put the cylinder here, then of course this cylinder automatically covers this cylinder which is here. So actually you need a coupling between biaxial order and the octupolar order. Actually, you can easily play with the tensors and show that if you take a quadrupolar tensor which comprises biaxial and uniaxial part, contracted with the biaxial, purely biaxial tensor, and with octupolar tensor, then you can get a totally anti-symmetric tensor, which I denoted psi ijk, and this psi ijk, as shown by Lubensky, can be the one producing the chiral. And it can produce ambidextrous chiral, because sign of B could be arbitrary. So that's the idea. And now we worked out some of these ideas. Namely, we elaborated a very simple model. Namely, we just took into account the previously discussed dispersion model. That's this one. So I have my biaxial quadrupolar field, and we added octupolar tensor and constructed interactions between these. Important assumptions that we took was we assumed that twofold axes of octuple tensor and the quadruple tensor coincide. Of course, that does not need to be the case, and deviations from that can be studied. But actually, suppose we limit ourselves to this simpler case. Clearly, one should add cross-coupling terms, but because these tensors are of different rank, you need to couple them with the radius vector between the molecular centers. So it involves the direction on the lattice. And of course, then discussion of the thermodynamics is a little bit difficult, especially for this sort of treatment. In the proper thermodynamics should also involve the parity degree of freedom. Clearly, I may have a population of left-handed and right-handed molecules, so I need to somehow weight these configurations. So there is an extra parity degree of freedom which has to be included in this treatment. And therefore, the statistical mechanics is a little bit more interesting than usually. Namely, it has discrete degrees of freedom and orientations involved. And we studied this model in this set of papers. Now I'll show you some results. First of all, you observed with this simple model, you can generate actually all majority of structures that are present, but that were shown by Lubensky and Jagiellonski. Actually, you can generate practically all structures that do not involve dipoles. So adding dipoles with this simple treatment would probably cover the whole diagram. So without dipoles, you get, of course, isotropic phase, uniaxial phases, you get biaxial phase, biaxial nematic, and you get a new structures which combine tetrahydratic and biaxial order. And that's NT star, that's the chiral structure. And you also get a new sort of structures which are referred to as nematic tetrahydratic, where a uniaxial quadrupolar tensor is combined with octupolar tensor. So that's what you get for some sort of parameters. We investigated the parameter space very carefully, and in so that was for tau equal 1. So for relatively small value of this new coupling, if you go to higher couplings, then first you get tetrahedratic, purely tetrahedratic phase, and then you again recover all the structures mentioned before. And apparently there were some experiments recently reported, most probably that tetrahedratic, nematic tetrahedratic phases were detected in these systems. But these are single experiments, so it's difficult to judge. Now, if we have cariality, then of course we have antisymmetric tensor. And having antisymmetric tensor, epsilon alpha beta gamma, means that we have local twist. So actually, we need to add higher order cross-coupling terms in order to properly describe the system. Actually, these results I've showed you were valid in the limit of low periodicity of, say, in the limit of infinite periodicity of the twist order. In order to get true situation characteristic of chiral systems, you need to add cross-coupling terms. And this cross-coupling terms involves Q tensors, and it involves octupolar tensors. And if you add something like that, you find immediately that your ground state configuration becomes twisted. And the twist depends upon the sign of octupolar tensor. Now I will show you some of our recent simulations on that. Then we did simulation in this area of the diagram, and more precisely, we carried out simulation for lambda 0.3 and tau equal 1. And at low temperatures, we got a holesteric phase. On increasing temperature, you see the appearance of dislocations. The color coding is for cariality. So this is left-handed or right-handed domain, and this is just opposite domain of opposite cariality. So you see here homocarial structure, which as temperature increases gets into ambidextrous cariality. And here is around the phase transition where you see clearly the appearance of multi-domain system, I think characteristic of the experiments for nematics. And here is completely disordered phase. Now, I still have 1 minute, right?
1 minute.
Okay, so that's perfectly all right. Now let me explain you how this model can take into account actual splay band deformations. And again, this is pure symmetry. So suppose indeed that tetrahedratic order parameter is relevant for the chiral problems. So T alpha beta gamma, totally symmetric and traceless tensor is one field. And we have also polarization field, which I omitted in my analysis, but it appears to be important. So we have also P alpha. Now, if I go back to my previous Hamiltonian, chiral one, let me go back. Ooh. Sorry. I still have half minute, right? Oh, it's always, challenging to find the transparency that you had before, but that's the one I wanted to show you. So let's disregard this red term, the pure cariality, and concentrate on the gradient terms here. On this one and that one. You see immediately that if you have all three tensors that coming into play, then this term couples with the tetrahedratic order by symmetry. So I have just this term minus, say, tau t squared. By symmetry, this term is allowed. If you compare number of legs, they match. So I have the coupling of this sort, which when expanded gives me something like here. So in the limit of the director picture, from that I get splay, bend, and twist deformations. I can get them. So this tensor gives us splay, bend, and twist in principle. Now, if I do the same trick here, you see this has only one leg, so it can be actually modified by the polarization field. So I get divergence of Q minus P squared. And this can generate splay and bend deformations if I do the analysis. And actually, this sort of formalism, which was proposed by Tom Lubensky, should explain, actually, in principle, this is one possible explanation of the experimental facts. Thanks a lot. That's all.
Thanks very much. I think actually that the symmetry argument is quite illuminating, even though it was very brief. We have time for one quick question. Jonathan.
So I'm trying to imagine a two-dimensional version of this theory, because I think everything will be so much easier to see in 2 dimensions, right? In that case,
except for one thing, you have different symmetry. You mean 2 dimensions and 3D tensor, right?
No, 2-dimensional tensor, 2-dimensional universe, right? Because in that case, your quadrupolar interaction is like cosine 2 theta, and next order interaction cosine 3 theta or 4 theta, right? And somehow I vaguely recall that Osipov did something sort of like this a long time ago. And is it something
Really?
Sorry?
I'm not sure.
Something like that with a lot of triangles. And
Well, we did 2D chirality index, but it
Right.
was nothing related
it
to
wasn't
this.
that. No, it's a
No, but okay,
I'm going to give you credit for it.
Sounds like a discussion for
okay.
tea break.
But I can comment your question on 2D systems.
Okay, please.
Actually, in this case, 2D systems are quite interesting because you have these discrete Ising-like degrees of freedom. So actually, you can have Ising-like phase transition in 2D, you know, from non-chiral to chiral structure. So it's a new aspect which is quite, I think, interesting. So you, of course, can get Kosterlitz-Tholes and all this business as well, because you have also breaking of continuous symmetry. But at the top of that, when going from non-chiral to chiral, you can get actually the full Ising sort of picture. Oops.
All right, let's thank Lech again.